All right, and here we go.
So, last time, I left you with a linear programming problem. Linear programming problem. So, basically, this was the problem of maximizing or minimizing a linear function over a feasible region. Reduced by linear constraints. Linear inequalities. Okay, so that's called a linear programming problem. So I asked you to maximize a certain function. But before we get to that, here's a theorem that might help you out. Which I'm not going to prove, but I'm going to use an example to suggest to you why it would be true. It says the following. The optimal solution to a linear programming problem will be found on, there are two main cases. For bounded regions, so remember that's just a region that you can fully enclose in some circle of finite radius. For bounded regions, you can find it on the corner points or an edge. Turns out for bounded regions, you can always find an answer. There's going to be some value that will make what you want work out. And if it's bounded, this value will either occur at a corner point or along an entire edge of the feasible region, guaranteed. For unbounded regions, it's a little bit dicier. The max and or min may not exist. In other words, your linear programming problem might not have an answer. It either does have an answer, it will again occur at a corner point or on the boundary. Now, why would that be true? Let's actually think about it. Why? Here's an illustrative example. Say f of xy equals x plus y was our objective. So here's some linear function. F is going to be the output when I plug in some x and y value. So now consider different outputs. So say f equals 1. which means you'd have x plus y equals 1, or say f equals 5, you'd have x plus y equals 5, or say f equals minus 3, you'd obtain x plus y equals minus 3, or just in general f equals any k, you'd end up with x plus y equals the k. Now, what are all of these? What do all of them have in common? What are they? Huh? Yeah?
Integers?
It doesn't have to be an integer. I could have said f equals a half. I would end up with x plus y equals a half. What are all of them now? I remember we're doing a geometrical approach, so think geometrically. What is that? Geometrically, what does it mean to say x plus y equals 1? What am I talking about? They're all just lines. They're all just straight lines. Every time my objective function outputs a value, this can be pictured as just some straight line in the plane. These are all lines. Which means, let's say I'm drawing the xy plane. Then, when my function outputs a value like 1, what does that mean? It induces a line, the equation of a line that goes like x plus y equals 1. So we'll just go like this, passing through 1. X plus y equals 5. Be a line that goes like this, passing through 5. And minus 3, right? It's going to be a line like that. In other words, I can just think different values of x, of f, will just give me different lines that I can go all over the plane with. There's an infinite number of possibilities depending on what output I'm looking for. Now, here's the idea. Suppose there is a bounded feasible region somewhere in the plane. So, here's a feasible region. How can I make sure f has the largest possible value on this feasible region? What would actually have to happen? Would this be the largest value represented on that feasible region? Well, the answer is no, because I can shift the line up, right, to say 6, and I get a larger value running through that feasible region. And you can say, well, you can just actually keep doing that. Just keep shifting the line up. Eventually, you'll get to a point where if you were to shift up any further, you would leave the region, right? And at the same time, if you're shifted down any further, you'll now get something smaller than what you had before. So it turns out the best value, the value that's going to give you the largest value, is going to occur on the edge. Now, depending on how the edge looks, if it hits a sharp corner, that's going to be a vertex. But if it's a straight line along that edge, which could also happen, that's going to be the entire edge is going to be the solution. Similarly, so here's where the max value will occur. Similarly, if I wanted a minimum value, all I do is just shift the line down. Eventually, I'll get to a point where I can't shift it down anymore without leaving the region. And so that's also going to occur at the edge. So it turns out that the edge is always going to be the solution. So, but the edge could itself be a line that's running parallel to this. So in that case, every point along this line will be a solution, or it could just be like a sharp point where only that point is touching the edge. And so that's why the answer to a linear programming problem is always going to be on the edges. It's going to be at the boundary. It's either going to be at a sharp point, or it's going to be along an entire line running along the edge. Because if you're not in that situation, it means you can move your line up or down to get a better value. So that's the easy case. So whenever I need you to find, say, a maximum or minimum, it means you don't have to check an infinite amount of cases. Just check the guys that are along the edges. Check all the corner points, and then check all the, and if one thing, how do you know when an entire edge is a solution? Well, that means if two corner points give you the same value, then everyone in between them will also give you that value. So that way you know that, oh, this entire line right here is going to be a solution. Other than that, just check the corners. So we go from a situation of there's an infinite number of points in here, but only a few of them actually matter for our problem. Now, if you look at, so for this, it's a bounded region. The maximum and minimum always exist. Just shift up until I'm about to leave and just stop there. In the unbounded case, this won't work. And that's because you can end up in a situation where you could be shifting up or down forever. And you'll never actually exhaust the possibilities. So let's say this time, my feasible region is the entire first quadrant. X greater than 0, y greater than 0. Then, if I'm looking at these lines, sure, there's a point where I can hit a minimum at the origin, but notice that there's no maximum. Every time I shift the line up, I'm still contained in the region, and I can go higher, and higher, and higher. So this would have no max. But min is at 0, 0. Because I can shift up forever. It will never give me a largest value. Right? So when things are unbounded, you can either have no maximum or no minimum or neither. But once things are bounded, you're guaranteed to have a solution. There's an answer out there that's going to fix this situation. Just shift up until you can't anymore, or shift down until you can't anymore with the line. So the last problem I left on the board, we were in the bounded situation, which means there is an answer that maximizes that function and at the same time satisfies all the requirements from our linear inequalities. So this is kind of why, and it's not a proof, but I think it illustrates well why this idea would be the way to go. So when it comes down to maximizing or minimizing, all we need to do is worry about the corner points. That being said, let's actually jump into the problem. Let me remind myself of what it was. The problem was to maximize given the constraints that 2x plus y must be less than or equal to 22, x plus y must be less than or equal to 13, 2x plus 5y must be less than or equal to 50. Your x and your y must be greater than or equal to 0. So those were the constraints. So these are some restrictions that I have. This is a function that I care about and I want to make it as large as possible. What is the largest possible value that this function can take on if I obey all of these restrictions? So, we're going to solve these. Step 1. Sketch the feasible region. So, that's what we're going to do. Okay. Sketching the feasible region means I'm sketching my constraints, given the constraints. So I'm going to sketch each of these linear inequalities. Now, of course, the easiest one to get away with are the x equals 0 and y equals 0 lines. So let's get those out of the way. So this is x equals 0 and y equals 0. And I know I want to shade in that direction, just be above this line and to the right of that line. What about this one? How do I draw this one? What do you do when you want to sketch the line? Find the intercepts. How do I do that? Plug in zeros for x and y respectively. So if I plug in x equals 0, I get y equals 22. I think that's going to be the largest y, so 22 is where it's going to pass through. And if I plug in y equals 0, I would get x equals 11. Just call that 11. And so there's this line right here. So now This is the 2x plus y equals 22. So that's that line. Then I'm going to do the other one. This is going to be x equals 13, y equals 13. It's just that at 13. Don't have to draw a scale here. It's 13. So you go like that. So this here is x plus y equals 13. Now I'm going to have to draw the 2x plus 5y equals 50. If I plug in x equals 0, the y will equal to 10. And if I plug in y equals 0, the x will equal to 25. So that will probably look like that. Not drawing a scale, I could never get that line properly. Okay, so this is 2x plus 5y equals 50. Now, there are times when you're not sure if the line should go where exactly it will hit corresponding to the other lines. So what you'd want to do is you want to find what the intersections would be anyway. So we're still in step 1. It involves finding the intersection. Let's actually intersect, say, the x plus y equals 13 with the one I just drew just now, 2x plus 5y equals 50. So let's look at that intersection. So that's just a 1, 1, 13, 2, 5, 50. So I can have 1, 1, 13. Row 2 minus 2, row 1. 0, 3, and that's 50 minus 26, what is that, 24? So this means your y would equal to 8, and your x plus 8 must be 13, which means your x is equal to 5. So it means that this location here will strike at 5, 8. So that would be 5. This will be 8. Yeah.
On like the test, if you ask if like the goal is to maximize a function, do we have to use matrices to? Okay.
Just find this however you can. That's besides the point. I mean, we're still in step 1. You don't have to go too crazy. Okay, let's find now where the 13, x plus y equals 13, intersects with the other guy. 2x plus y equals 22. So that leaves us with 1, 1, 13. And this is 2, 1, 22. So 1, 1, 13. And then I can take row 2 minus 2, row 1 minus row 2. 2 times this minus that is 0. 2 times this minus that is 1. 2 times this is 26. Minus that is 4. So y equals 4, which means that x plus 4 should be 13, which means that x will equal to 9. So yeah, I think we hit these in the right position. So this is the xy plus 13 hit with that one, so it's over here, and the x coordinate is 9, which makes sense according to the picture. If you learned that, for example, that the x value for this one was larger than the x value for that one, what it means is that you intersected at the wrong time. You should actually go below and hit that one first. So that's 9 and 4. That's that one. And finally, let's do the last one. So I want to know where this intersection happens. That's the 22 line. That's this guy intersected with this guy. So I have the 2x plus y equals 22, and I have the 2x plus 5y equals 50. This leads us to 2, 1, 22, 2, 5, 50. I can take 2, 1, 22, take row 1 minus row 2 minus row 1. This minus that is 0, this minus that is 4. 50 minus 22. 20 what? 4 goes into 28, right? So this means that your y is going to be 28 over 4, which is 7, and your x, and your 2x plus the 7 should be 22. So this means that your 2x is going to be 22 minus 7, 15. So x is going to be 15 over 2. So for here, it's going to be at 7, comma 15 over 2. It's going to be 7.5.
I'm sorry, that's the only one I had.
Huh? Come in?
No, he was borrowing a pencil.
What?
Were you talking to?
Yeah, I heard
Yeah.
something wrong.
Oh yeah, he was borrowing a pencil.
Okay.
Yeah.
Right. Okay, so all those intersections in relation to each other look right, so that's the right picture. And now I'm going to figure out what is the feasible region. Now, these are all less than if I were to solve for the y, which means I need to be below all of these lines. So I want to be to the right and up, but every other line present, I want to be below them, which means that that's my feasible region here. That's under this line, it's also under this line, it's also under this line. So it forces us over here, which means there are a couple more points of interest. Didn't even care about that one really. This one, that one, and that one. Okay. But these are easy because they're actually intercepts. So this one is going to be 0, 10. This one is going to be 0, 0. And this one is going to be 11, 0. So that's step one, which you can drive too quickly, very quickly. Probably in a test I won't give you this many lines, but that's how we would start the process. And so now what we can do is step 2. This means find the corner points. Done. Okay. So a lot of them you'll actually find in step 1, but you might have to find extras. So here were some extras that I filled in. Those are done. And now step 3. Evaluate f of xy at each corner point. Because, again, you know from that theorem that the answer to the problem is going to occur either at an edge or at a corner. So, so if we look at what was the original function? X plus 2y? Yeah, x plus 2y. If you were to sketch that, you would get a line of negative slope. So, I mean, common sense kind of tells us that the answer is going to be like this guy, maybe that guy, but it seems like this guy. But you want to make sure that that's going to be the case. So what you're going to do, the nicest way to do it, I think, is to just set up a table. Set up your x and y values, and then compute your f of xy values, which is going to be x plus 2y. Yes, x plus 2y. So How many points do I have to worry about? 1, 2, 3, 4, 5 in this case. So 1, 2, 3, 4, 5. So we have the origin, 0 and 0. We have 11 and 0. We have 0 and 10. We have 5 and 8. And we have this guy, the 4 and 9. And all you're going to do now is you're going to literally just plug these values into that function. So if I plug in 0 and 0, I of course get 0. X is 9, y is 4. Yes, that could actually mess things up a lot. Okay. So the x is 9, the y is 4. Okay, 0 and 0, I get 0. Here, if I put in 11 plus 0, that's just going to be 11. Here, 0 plus 2 times 10, that's going to be 20. Here, 5 plus 2 times 8. 2 times 8 is 16, plus 5 is 21. Here, 9 plus 2 times 4, that's 9 plus 8, that's 17. And so because we wanted to maximize, that's the guy. He's the largest one at a corner point. So that's the solution. So that's step 4. I'll get to you. Step 4, conclude based on step 3. So for example, here I would say something, the max f is 21 and occurs at 5. Yeah, what was your question now?
So if it's like the feasible region is bounded by like not a dotted line, not a solid line. Like,
Yeah.
Can you use the corner part or no? Like say.
Then no.
Yeah.
You wouldn't be able, because technically you wouldn't be able to touch it.
Uh-huh.
So you would then end up in a situation where you're like, if it's impossible for you to touch it, and that's where the answer is going to be, you'll probably just say, get as close to it as possible without triggering some other negative consequence. But the problems that I'll be asking you to do, they'll always be solid lines. So you probably don't have to worry about that as well. So any other questions on the process? Yeah, so I'll give you a function like this. It's going to be a linear function. I'll give you some constraints. And you're going to figure out what is the best location within those constraints that will maximize or minimize the function. Or to state it more correctly, what I will do is I will give you a word problem, which you are going to read, and you are going to figure out what is the objective and the constraints. Then you're going to do this. Okay. Which is a lot, so we're going to do some practice. So we're going to go through these guys, which we definitely won't finish today, but by maybe next class, hopefully we'll be done with that. So the level of difficulty that you can expect on like a test might be slightly lower than this, but it's a good idea of what can go on. Right? So this is how a linear programming problem is going to be presented. It's going to be a word problem. And you are going to actually have to figure out how to translate it to a linear programming problem and then solve it via this process. So let's jump into the first one. And I posted an electronic copy of this on the class webpage, so if you lose that, you can find it again. to get there. Okay. So animals at a rescue center must have at least 30 grams of protein and at least 20 grams of fat per feeding period. So that's what consists of a healthy diet for them. The shelter has two kinds of food, food A and food B. The components of food A amount to 2 grams of protein, 4 grams of fat, and it actually costs 18 cents per unit to purchase food A. Food B has 6 grams of protein, 2 grams of fat, and costs 12 cents per unit. Now, food B is bought under contract requiring at least 2 units of food B per serving. So maybe that's why you could get it for cheaper. You're promising that you're going to buy a certain amount because you'll have to feed at least 2 units per serving. But there's another contract that requires the amount of food B used per serving not exceed 3 times the amount of food A for whatever reason. You know, maybe food B is actually of a lower quality, which is why it's cheaper. And then PETA came in and be like, you can't serve the animals this. You know, make sure that you give them the good stuff and don't exceed with more than 3 times this, right? So you're like, okay, fine, right? So that's the thing. You have a contract, you have to buy a certain amount of food B, but then you can't really serve more of food B than food A in excess of 3 times the amount of food A. So now the question is, how much of each food should be bought to produce the minimum cost per serving? And it turns out that's a linear programming problem. And it's a linear programming because there's not really equations, there are inequalities that are involved because you have to be less than something or at least something. So the first thing you're going to do is you're going to translate that into math speak. So, 1, what's your objective? Well, the objective is to minimize cost, right? So now the question is, what is the cost function? So what would be the cost per serving here? Minimize cost per serving. Well, what's cost per serving?
0.18 A, or 0.18 and then the number of units of A.
Yeah, let's call it X, just to be suggestive because we're going to start plotting this. And
0.12
0.12b, or let's call that y, where x equals number of units of A per serving, and y equals number of units of B per serving. Okay? So I set up some variables. Let x measure the amount of servings of A, y measures the amount of servings of B. My cost is therefore this equation, which I can think of just as some linear function. Cost is going to be linear in this case. And the goal is to make that as small as possible because you want to help the animals without going bankrupt, right? You need to be able to keep the lights on. So that's what we want to minimize. Now, what are the restrictions? Okay, so let's begin. How do you figure out what's the restriction here?
The contracts are the restrictions.
The contracts, actually the first sentence also has a restriction. Right? Every serving has to have a certain number of, a certain kind of macro split here. You need 30 grams of protein and at least 30 grams of protein and at least 20 grams of fat per serving, yeah.
2x plus 6y has to be greater than or equal to 30.
No, be careful of how it's listed here because that's 2 proteins.
3x plus y is to be greater than or equal to 30.
Oh, you're doing the protein. So yes, that's actually correct. So look at the protein, look at these one at a time. And yeah, it's going to be 2x plus 6y must be greater than or equal to 30, right? So this here the 2x is the protein from A. And here's the protein from B. Right? Because I know I'm serving X units of A, each unit contains 2 grams of protein. And if I'm serving Y units of B, each unit contains 6 grams of protein. So the total amount of protein is going to be that. And I need that to be at least 30, which means greater than or equal to 30. I can do a similar equation inequality for the fats. And the amount of fat in food A is going to be 4 grams per unit. And the amount of fat in food B is 2 grams per unit. And that needs to be at least 20. So that represents here total fat content. Okay, so that's from the first sentence. The first sentence gave us 2 restrictions for proteins and fats. Moving down, let's talk about the contract. Food B is bought under contract requiring at least 2 units of B per serving. What does that mean? Yeah.
Y is greater than or equal to 2.
The Y must be greater than or equal to 2. This is by contract on B. Another contract, the amount of food B should not exceed 3 times food A. What does that say?
So y is less than or equal to
Y should be less than or equal to 3x. That's the contract on A. Now there are a couple more that we can throw in here. X must be greater than 0, and of course Y must be greater than it, or is it equal to 0. And of course we're taking positive values here, because you can't serve negative units of something. So these are almost always automatically thrown in, depending on the situation. So even if it's not specifically mentioned, it makes sense here that they would have to be greater than or equal to 0. That helps us to bound the region. Without that, it might not be bounded. And it makes complete sense here to actually bound the region, because you can't go too much in the opposite either direction. Yeah, that's all the restrictions. So you read this problem, and your friend who owns the animal shelter comes to you and says, I don't know what to do. You're like, calculate all this and tell him what to do. Okay, so this is the situation. Want to minimize this function in the presence of these constraints. And that's a linear programming problem, because that's a linear function. These are linear inequality constraints. So step 1 is going to be, we want to sketch the feasible region. So we have our x equals 0, we have our y equals 0, and we want to be to the right and above that. We have a y equals 2. It's just a horizontal line passing through 2. We have our y equals 3x, so that's just going to be a line going through the origin. That, and it'll hit here. Y equals 3x, that'll hit at 1.5, 3 over 2. Sorry, 2/3. Because the y is 2, so the x will be 2/3. Okay. That takes care of all the bottom ones. Now let's get to the higher ones here. Let's say we do the top one. So we would have here, if I solve for y, plug in x equals 0, solve for y, that would be 5. Plug in y equals 0, solve for x, that would be 15. I think that's going to be the largest x value present here. So we're going to have that. This is 2x plus 6y equals 30. And then I'm going to have the other line Plug in y equals 0, our x will equal to 5. Plug in x equals 0, our y will equal to 10. Now, at this point, I'm sufficiently confused as to where exactly this is going to land. So what I'll start doing now is finding some intersection points, figuring out where is this guy going to touch that versus this, and to kind of know that I'm positioning things correctly. So let's start looking at, because you're not going to scale, so it's going to be hard to know when you're doing the exactly the right thing. So let's find some intersections here. What about, well, we already know this one. What about this one here? That's where the y equals 3x intersects this guy. So this means that 2x plus, I can plug this in here. This is 18. So I have 20x equals 30. So x will be 3 over 2. And y would be 9 over 2. That's 3 times x. So 3 over 2 is definitely less than 5. That's going to be 3 over 2. And the y will be 9 over 2, which is 4.5. So that's going to be below here, 4.5. That makes sense. Let's find this one. Y equals 2 intersected with the other guy. Intersected with 2x plus 6y equals 30. Again, I can just plug in the 2 here. This means that 2x plus 12 equals 30. This means 2x equals 30 minus 12. It's 18. So x equals 9. There's 9. Now let's do this guy. Intersected with y equals 2. This means that 4x plus 4 equals 20. 4x equals 16, so x equals 4. So that guy has to hit before, like after here, it's going to do 4. Okay, so there's going to be something touching here. What about the 4x plus 2y equals 20 intersected with the other guy? 2x plus 6y equals 30. I can reduce the top. 2x plus y equals 10. That 2x plus 6y equals 30. What I can do is take the row 2 minus row 1. I would get 5y equals 20. So your y would be 4. And so then I would have 2x plus 4 equals 10, so that your x will be 3. So that guy is going to hit this guy over here, right? Is that right? I think that's right. Okay. So, it's going to be 5 here, not drawn to scale obviously, 10 here. So, let's move this. So this is going to occur at 4. So it's going to hit here. This is going to occur at 3. So this is 3, 4. So that's our situation. What is the feasible region? I need to be above this, above that,
It's like the right, the base.
below this, above that. So it's going to be like this, it's unbounded here, right? That's it. So these are the corner points. Now again, looking at our objective function, we understand that it's going to be a line that's slanted this way. So it's not actually going to have a max. You can spend all the money on these animals you want, but there will be a minimum point that you can spend. And so let's actually find, do we know what this is? So this I know is 9, 2. This we know is 3, 4. Do we know this? Did we do this? No. So I would look at y equals 3x and intersect that with this guy, the 4x plus 2y equals 20.
It's 2, 6.
Huh?
It means 2, 6.
So, right, plug this in here. That will give you 4x plus 6x equals 20. So you have x equals 2. Then you would have y equals 6. So this is actually 6, 2 right here. So now that leads us to the next phase. Where we are going to just do the test. X, y, and 0.18x plus 0.12y. The options are 6 and 2,
It's 2, 6.
2 and 6. And 3 and 4. And 9 and 2. So at this point, just reach for your calculator, compute these. What's the first one? 0.18 times 2 plus 0.12 times 6. Times 3 plus 0.12 times 4. 0.18 times 9 plus 0.12 times 2. What? Ah, so now we know what we should be aiming for. This. So this means min cost is going to be $1.02 per serving. Serving 3 units of A and 4 units of B. And that will be the minimum cost. That's the best. It's the best way to actually do it. This is the cheapest way to feed the animals the macros that they need and at the same time obey all contracts. Each meal must have that composition. Questions? So it's a bit of a marathon, but hopefully the process at least is clear. Just try to do a little bit more practice so you get faster at it. Not really a math question, more like a business question. Probably hard to actually fish for a nice answer here without actually giving it away. So, what you would notice from this solution, just in case you were really worried about keeping the lights on, is that you have 4 units of B, right? That's the best thing for you. You would also notice that in the contract, you're only required to sell 2 units. So you negotiated some price based on the fact that you're going to be buying 2 units per serving. But in fact, you are buying more. So when you realize something like this is the solution to a linear programming problem, right? Either you do the math or have one of the mathematicians in the dungeon do it for you, and they come back and report to you, this is the answer. Now you as the business person is going to be like, you know, we can make the situation even better, right? A good idea would be to renegotiate the contract on B. So what you're going to do, and you're going to go to the supplier B, and you're going to be like, I'm going to buy double of what I normally buy. Oh, you're going to buy double? I'll buy double. Just give me a little discount on the price. Now, unbeknownst to him probably, it's actually better for you to buy double, right? You go, you know what? I want to double my order. Maybe just knock it down from 12 cents to 10 cents or something like that, right? Then everybody wins. He gets to sell more of his product, and you actually get to obey all the contracts that you have and still get the best price for you. So that was some sort of thing to think about, although that's not really direct from the math here. That's just a little thinking outside the box that I wanted to mention. So how about you guys trying your hand at one of these, and we can do it together. Try 3. I think that's the shortest one of all the ones that are left. Two is also pretty short. Try it. Well, compared to this, I mean. feel like you should make it more than halfway through this by now, so let's actually just get started. So, one thing we're going to want to do, let's look at our variables. Company is considering 2 insurance plans with coverage per unit and premiums shown below. Policy A, $10,000 per unit for fire and theft, $180,000 for liability, and the premium is $50 per unit. Policy B gives you $15,000 for fire and theft, $120,000 for liability, premium is $40. You want at least $300,000 in fire and theft insurance and at least $3 million in liability insurance. How much of each plan should be purchased to minimize the cost of premiums?
Say X equals number of units of A. Y equals number of units of B.
This means that the premium cost is going to be what? Right, so it's going to be 50x, because it's $50 per unit x, plus 40y. That's my objective function, want to minimize. Then now we're going to look at our constraints. We want a certain amount of fire and theft insurance, and we want a certain amount of liability insurance. Those are the only 2 things they're looking for. So the fire and theft insurance from A is $10,000, so there's going to be $10,000 per unit of A bought and $15,000 per unit of Y bought. And we want the fire and theft to be at least greater than or equal to $300,000. For liability, A has $180,000 per unit. B has $120,000 per unit. Oops, no zeros there. And we want that to be at least $3 million. That's the situation. There's no other. Well, we have again. These are automatic. Greater than or equal to 0. So now, what we're going to do is we're going to figure out the diagram. So, if we look at, of course, the x greater than 0 and y greater than 0, it's going to be those guys. In the first line, if I plug in, say, y equals 0, x is going to be 300,000 minus, divided by 10,000. It's going to be 30. And if I plug in x equals 0 to solve for y, the y is going to be divided through by the thousands. And 15 into 30 is going to go 20. 20. So this is going to be that's going to be the 10,000 x plus 15,000 y equals 300,000. And then you do the same thing over here. So 3 million divided by 180,000 was what? I don't think that went into it exactly. Yeah, 16 and 2/3. I think I got a similar thing. So it was 16.67. And the other one, what was up here? 25. So then that's that. So this is the 180, 1, 2, 3x plus the 120, 1, 2, 3y equals 3 mil. So now I want at least, which means I want to be above both lines. So that leaves me with a feasible region. Again, it's unbounded feasible region, which might start out by being alarming, but then you remember you're looking for a minimum. So So that's actually going to be okay because the line is actually slanted this way. It will have negative slope if I plug in a value for f. So moving it up, I don't care about moving it up. I actually want to move it down as much as possible. And so points of interest are going to be this, this, and this. And what was this? So I need the 10,000 x plus the 15,000 y equals 300,000. Need 180,000 x plus 120,000 y equals 3 million. I can divide through by the thousands. I can also divide through by 5 again. So this will, the first one is actually 2x plus 3y equals 60. That's this equation. Here I can divide through by 10,000. I can again divide through by 6, right? 3 6 is 18, so that goes into 3 times. 6 goes into that 2 times. And 6 goes into this 50 times. So it really reduces to that. What I can do is say, multiply this by 3. Multiply this one by 2. Okay, the top one minus the bottom one, I would get 5y equals 80. So my y would be 80 over 5, which is going to be what? 16. And my x would be what? 11.3. And so now I'm just going to do all the checks. X, Y, and the, what was the premium? 50, it was 50x plus 40y. So I have the option of buying none of the x's, 25 units of the y, or 16 of the y's, 11.3 of the x's, or 30 of the x's and none of the y's. Can you see what these were? What were those? You got 1,500?
1,000.
Huh? 1,000 flat?
And 1206 and a half.
1206.
0.5.
Okay, so the winner is this guy.
I got 6. Cool.
What?
I was like,
Oh, no, switch those two. The second one and the first, I wrote something.
if Y is 16, I think X is 6.
Yes.
Oh,
I had 30 at first.
okay. So what
For the
is
bottom one, I got 15.
940.
this is 940,
Yes.
and what did you get for?
The bottom one was
1,500 and the top one is 0.
Yeah.
This is 1,500. Top one is 1,000. Okay, so that's still the actual minimum, $940. And we get that by buying 6 units of policy A and 16 units of policy B. We'll stop there. We're actually running over a few minutes. Try the other two.
I did read it. This is the first time you've done it. I can talk about it.
Try the other two, and I'll see you guys next week.
You're right.